Welcome. I'm Benjamin Ang. I'm a Senior Fellow and Head of Future Issues and Technology Research Cluster at RSIS. And for those of you who are new to us, RSIS, Rajaratnam School of International Studies, is a global graduate school and think tank focusing on strategic studies and security affairs, with 5 research centers and 3 research programs, of which one of them is Future Issues and Technology. And RSIS as a whole, the think tanks conduct policy relevant and forward-looking research in national security and international security, science and technology, society and economic and environmental sustainability. And one of the key things that we have been looking here in our research cluster of future issues and technology, or FIT for short, is to support the RSIS overall research agenda on emerging issues where science and technology are intersecting with national security. And to do this, we have been collaborating with a wide range of stakeholders in RSIS, as well as outside of RSIS. And we're very happy to have here not only our own Dr. Carol, who is a research fellow in FIT at RSIS, but also Dr. Yuna, who is the research fellow at the Earth Observatory of Singapore, EOS, at NTU. And together, they have written an excellent report, which I hope you will read, on this issue of AI and space, and how, as Singapore has been treading steadily towards integrating AI with space technologies, they are sharing what they found about the potentials and challenges and policy implications of AI in advancing space technologies with a focus on sustainability for both Earth and outer space. So I actually recognize some familiar names from the AI community and some familiar names from the space community. So welcome you to this webinar where we'll bring together both of these very, very interesting fields of research. And they'll be talking about how AI's role is in extending satellite life, mitigating space radiation, climate change. And but don't listen to me. I want to hand you over to our very excellent panelists, Dr. Carol and Dr. Yuna, and please give them your full attention. And the meeting today is being recorded, but we are not recording the Q&A. So feel free to ask whatever questions you want under the Q&A. If you don't want your face to appear in the recording, you can always switch off your camera. But it will be recorded so that in future you can refer back to this webinar. But for now, please, over to the panelists.
Thank you, Ben, and thank you everyone for being here. I know a lot of us are already on holiday mode, so we truly appreciate you taking time to be here. We also thank the Center of Excellence for National Security and RSIS for their support in this event. So today we will be talking about what happens and what could happen when AI and space converge, with emphasis on sustainability both on Earth and in space. So as Ben mentioned, today's webinar will be based on a recent policy report, and if you have time, you can go through this report as well. So I have co-authored this with Yuna here, but also Sean Chua, who was a master's student in RSIS at the time. So our findings were informed by interviews with space experts within the Singapore space ecosystem from the public, private, and academic sectors. And also, to manage your expectations, we should let you know that our interviewees did not talk much, understandably, on military purposes of space activities in Singapore. We do recognize its role, which we will mention later in our recommendations, and also to emphasize the sensitivity of some information. A couple of our experts, while they agreed to share information, they preferred to be anonymized. And that's what we did both in the report and for today's presentation. Okay. So today we will cover AI in space applications around the world. And I believe we need to preface today's discussion by acknowledging that Singapore is not at the top of the world in this domain. So I'm very sorry to burst the kiasu, the competitive bubble, but Singapore still makes for an interesting and unique case study, as we will outline in a while. So Singapore also has the potential to be one of the forerunners in the region, especially if momentum is sustained. But here we emphasize on one of the forerunners to be fair to the other space agencies in Southeast Asia with much potential as well. So he found three key themes on AI in space applications in the city-state, sustainability both in space and the Earth as strong driving forces, the opportunity for specialized equatorial data collection powered by AI, and that there is some synergy among the public, private, and academic sectors. So we will also discuss opportunities and challenges unique to Singapore, and of course, in true academic think tank fashion, policy implications and recommendations. Okay, so just to set the stage, there has been the first European Space Agency AI in and for Space conference held a couple months ago. I think it was in September. So of the 40 papers and 55 posters, none were from Singapore, although there could be a number of factors for that, including the conference being hosted by and held in Europe. So this conference is actually evidence that other countries around the world have been doing some research and development in AI in space applications, but AI in space, to be fair, is still also quite emerging, and AI remains on the brink of reaching maximum impact in space. So it's not quite there yet. So even in this conference, many ideas were still novel, a lot were still in the prototype research phase, and trends are actually yet to emerge. But there are some worth mentioning, including this one on the left. So this was a project funded by the Italian Space Agency, and they're creating a software for smarter space missions. So here they use AI to be able to process data on its own up there and make its own decisions while in space instead of sending large amounts of raw data back to Earth and then having the scientists analyze it like down here. So this makes missions faster and more efficient. And they are also creating software prototypes for scenarios, not just on Earth, but as you can see here in the picture, even exploration in Mars. So they're already there. So the first column here, the one on the left, are the extracted images, while the second column on the right are the ones with extracted features with further details. Okay, so another example here on the right proposes an algorithm that uses AI, specifically deep learning, combined with standard techniques to analyze landing areas. As shown on the figure here, this is the surface of the moon. And so the tech helps them pick a safe spot for landing. So this is important because typically during a spacecraft's landing, harsh terrains can cause it to tip over, and then this prevents its equipment from working properly. And currently, the hazard detection systems in place are not enough to accurately identify these dangers, especially if they're under poor lighting conditions. So here they show that the algorithm performed quite well, reliably finding safe landing zones even under these difficult conditions. Okay, so another one here on the left by the Aerospace Center of Excellence in the UK tackles navigation challenges for asteroid missions. So the problem is that the spacecrafts, they need to figure out their exact position relative to an asteroid to prevent colliding with it. But this is hard, again, when lighting is poor. So their solution here was to combine data from two types of sensors. First, they use the optical data sensors, which uses visible light, and then they combine this with thermal data sensors, which measures heat. And then they process it with the AI component, which is machine learning, to improve positioning accuracy. So they tested it, it's still in the prototype phase. So they tested it using synthetic images based on the European Space Agency's HERA mission to simulate real conditions, and found that these combined data from the two sensors did indeed work better. And of course, let's see if you guessed correctly. So this one is not a dog, it's not a rock, and it's not Trump's personal robot. It's actually a multi-arm robot designed for on-orbit servicing operations. So on-orbit servicing operations are performed by robotic or human controlled spacecraft to maintain, refuel, upgrade, or even construct other satellites or structures in space while they are in orbit. So you don't need to bring down the satellite and then launch another one. You can actually fix it on orbit. So this extends the lifespan and also the capabilities of satellites, allowing for more sustainable space activities. So for this project, it offers a solution to the unpredictability of space environments, which makes it more challenging for robots to move and operate using the more traditional methods. So here they combined AI in space by combining what they call trajectory optimization with reinforcement learning. So TO, the trajectory optimization, is the space component, which provides detailed pre-planned paths for the robot, while reinforcement learning, the AI component, learns from simulations to adapt to unexpected situations. So they tested this hybrid approach with this four-arm robot, and results were actually quite promising, with the robot following the planned paths more accurately and quickly being able to adjust to real-time changes. Okay, so I hope you're still with us at this point. I tried to explain those best I could as a social scientist, but less experimental and more real-world applications include using AI and satellites for mapping deforestation, predicting weather patterns, analyzing waste processing and recycling activities. So here specifically, they were able to identify around 86 tons of material on average that could have been recovered, that could have still been recovered, but are being sent to the landfill. So they also use AI in space to watch patterns of climate change and also emissions tracking by combining satellite imagery with data from machines. And this can potentially reduce emissions by 20 to 30%. So, we'll be talking more about these in a while, as this is the space where Singapore largely is in terms of AI and space technologies. Okay, so if we're not top of the world in these things, why do we still need to look at Singapore? So Singapore is actually a unique case, as it is a small, non-major space power situated in Southeast Asia. And with just those qualifications alone, it would already be good to highlight the Singapore case, especially in a subject matter where much attention is given to larger states with more and more mature space capabilities. So Singapore has a relatively young space office compared to those in Europe, North America, and even some neighboring space agencies in Southeast Asia. But we must say that it is a funded space office. So Singapore also has a thriving AI sector. And so it would be good to see how the AI sector feeds into the space sector. And as we have suggested in our report, hopefully vice versa as well. Singapore also has its own way of coordinating public, private, and academic space activities, which makes for an interesting case. However, there is a missing core element here, which again, we would like for you to guess, but there's no Menti here, so just keep it in your head, and we will reveal this to you later. Okay, Yuna, over to you.
Thank you so much, Karel, for setting the stage. That was wonderful. So now let's move closer to the Earth observation. So just imagine waking up one morning to an alert on your phone. An AI-powered satellite system informs you it has just detected early warning signs of the hurricane that is being developed off coast 48 hours before the traditional methods would have spotted it. So local authorities are already mobilizing, communities are preparing, and you can imagine hundreds of lives could be saved just because of this early action. And all because AI systems, AI-powered space systems are watching over us. And it's not really science fiction, it's something that is happening today. So every single day, the network of satellites generates and transfers to Earth around 2 petabytes of data about our planet. You can imagine that this sheer volume of data cannot really be processed by human analysts, and this is where the AI comes to help us. So before I guide you through the technical aspects of the satellites and how AI can enhance the operations on the satellites, I would talk a little bit about the theory. So Karel, can we please go to the next stage, to the next slide? And first, I want to tell you a little bit more about the different orbits that Earth has. So please don't freak out about this image. You don't need to read the words there. Just what you need to see is colors or the lines adjacent to the Earth. So the blue color that you see very close to the Earth, this is low Earth orbit. So Singapore usually launches a lot of low Earth orbit satellites, or in short, LEO. So I will use this abbreviation in the future. So LEO is normally an altitude of less than 1,000 kilometers, but could be as low as 160 kilometers above the Earth. Unlike satellites in the geostationary orbit, which is around 36,000 kilometers, these satellites must always orbit along Earth. The LEO satellites do not always have to follow a particular path around the Earth. Their plane can be tilted, so it means that they can serve a lot of different applications. This is why LEO is usually the commonly used orbit. It is commonly used for satellite imaging and for remote sensing, as being near the surface allows to collect the images of higher resolution and the data with higher precision. However, individual LEO satellites are less useful for tasks such as telecommunication because they move so fast across the sky, and therefore they require a lot of groundwork with the antenna. So antenna has always to follow the satellite, which is not super convenient. That's why the majority of communication satellites are situated on geostationary orbits. So a geostationary Earth orbit, or GEO, satellite is a satellite that is situated at 36,000 kilometers, and this is the green line that you can see. And so this satellite basically follows. So it stays in one position, and it allows the satellite to maintain the position with the specific geographic regions. So the satellites that are situated there, they are mostly telecommunication satellites, broadcasting, remote sensing, navigation, and a bunch of weather satellites are also situated there. So if we can go to the next slide, and I will talk more about the problems that satellites usually face in the space. And one of the biggest problems, as you can see from this picture, and it makes you frustrated, is basically space trash or space debris. So currently we are tracking around 36,000 of pieces of orbital debris, which is more than 10 centimeters in size. And I think currently we also track around 100 million pieces of debris, which is smaller than 1 centimeter. So you can imagine how much has happened. And actually this picture is also a nice representation of different orbits. So you can see the LEO low Earth orbit being highly packed with the debris, and you can see this thick white ring around the Earth. And also you can see this line that lies across the equator, and that depicts the geostationary orbit. And you can see there is less trash, actually. So the satellites in geo orbit are less prone for the crowding and space debris. So can we go to the next slide, please? And so one of the ideas to deal with crowded orbit and with space debris is either arranging the debris graveyards, and this is when the satellite is just removed to a higher orbit and just exists there before the technology is developed to come there and to grasp the objects. So for example, currently, there is one of the satellites that is going to be launched by European Space Agency, I think in 2025, and it's going to be launched to 500 kilometers orbit, and it will capture a big piece of an older satellite. So it will kind of absorb it, and then it will just be removed from the orbit, and it will burn in the atmosphere. So kind of, I'm not sure. So it's you're trying to remove the trash from the orbit, but at the same time, you're also developing the technology and you're sending more materials into the space. So it's this is a problem that needs some improving. So another solution to deal with crowded orbit is autonomous satellite maneuvering around debris, which is enhanced by AI, and we will return to this a little bit later. And something that Karel has already mentioned is the extended satellite, how to extend the satellite lifespan through in-space maintenance. Currently, there are efforts to develop the satellites that help that aid other satellites if they experience certain problems. But of course, it is difficult to predict problems that can happen in space. So another problem currently reported for satellites is high radiation. So you can imagine that environments with high levels of ionizing radiation, they create special design challenges. And a single charge particle can knock out thousands of electrons, and it can cause electronic noise, signal spikes, and in case of digital circuits, this can lead to the results which are inaccurate or unintelligible. So, and due to the low demand, you can imagine this is only space or maybe nuclear plants, the technology of radiation hardened chips tends to lag behind the most recent developments. So radiation hard processes include both physical treatment. This is shielding the chips or the circuits with shielding materials, which leads to the increased weight, or logical or computational, which this is when the several computing boards are used or the redundant bits are used into the programming. However, in this case, the size of the processing device increases 5 times. That also has to be accounted for when you calculate the payloads of the satellite. So several private companies in Singapore work on developing the algorithm to deal with the crowded orbit. And there are several collaborative projects that develop the shielding that allows to resist the high radiation in space. And we will return to this in the next slide. So can you please go there? So one of the examples that accounts for common problems and offers groundbreaking solutions is the satellite Elite, which is extremely low Earth imaging technology explorer, which is going to be launched to a very low Earth orbit of 250 kilometers in mid-2025. And it was constructed by NTU Satellite Research Center. It will be 14th satellite launched by NTU. So this altitude, 250 kilometers, is pretty close to Earth. It is relatively unexplored, and it means there are less trash, less debris, so less collision is possible. But at the same time, it is surrounded by highly reactive gases, and it is subject to atmospheric drag. So this satellite will be equipped with the first locally designed space camera. It will allow to capture better quality images up to 50 centimeters in resolution. 50 centimeters, this is just crazy. You can think about the geostationary satellites, those weather satellites, and their resolution is around like 50 meters. You can imagine the huge difference. So the atmospheric drag that is going to pull the satellite back to the Earth is going to be fixed by the introduction of novel fuel-efficient engine, which will just turn on the thrusts in order to improve the trajectory and bring the satellite back to its orbit. And this engine was actually developed by NTU spin-off in engine called Alena. So in this height, the satellites will encounter atomic oxygen. This is a highly reactive gas that corrodes and degrades electronic materials. And to protect the satellite from any adverse effects, the ultra-thin transparent nanotechnology spacecraft Coltin was designed by Temasek Laboratories in collaboration with NTU Satellite Research Center. So this is actually the good evidence of innovative collaboration between academic and private sector. And actually in the end of life, after a year and a half, after the satellite collects the information about the Earth, it will just go back to the atmosphere and burn. So it means it is sustainable. There will be no waste. So if we can go to the next slide. So how AI facilitates operations in space, and I guess Karel has already mentioned a couple of examples about the Mars and the Moon, but it also, AI proves invaluable for sustainable space and Earth operations. So we'll start with space operations first. So to help with crowded orbits and facilitate navigation, AI systems can early predict the potential collisions. They can automatically calculate the avoidance maneuvers. They can identify optimal time for debris removal missions. And then finally, some other options can be mapping safe corridors for satellite launches, as well as for satellite retreats when they go back, and then optimize power usage in space, provide predictive maintenance for critical systems, and ensure proper resource management. This is something that astronauts can benefit from. So that's enough about space. Let's see what's happening right now in the Earth, and can we go to the next slide? So what you see here is damage proxy map resulting from the volcano eruption that happened in November 2024 in Flores Island, Indonesia. This is Levotobi volcano. I'm sure that you have heard about this. So it depicts the areas that were likely damaged after the eruption. This map was derived by from a synthetic aperture radar, which is called SAR or INSAR. Which was acquired by the Copernicus Sentinel satellite operated by the European Space Agency. So it was prepared by EOS Remote Sensing Lab, and the damage is showed by colored pixels of 30 meters in size, where yellow to red indicate the increasingly significant ground surface change before and after the event. So preliminary validation of the damage was conducted using news reports, aerial imagery, ground level imagery, and videos in the damaged areas. So although it might look like a simple photograph with highlighted areas, however, the original raw satellite data is nothing like that. So it contains the data with the parameters that can be interpreted only using special remote sensing software. The parameters can be combined and verified, for example, with spatial data or with, as mentioned before, news reports or the data from social media. Only when being processed with in-house algorithm, there we get to see the interpretable and customizable images according to our needs. So unlike traditional optical imaging or passive remote sensing, which uses just the reflections of the sun radiation, synthetic aperture radar and the satellites equipped with it emit their own energy, such as radio waves, that is reflected back from the Earth and recorded by the sensor. So this is especially relevant for monitoring of the areas which are prone to being covered with clouds, which is Southeast Asia, Northern Europe, and South America as well. So multispectral remote sensing can discern many Earth-based features because different objects can absorb and reflect different wavelengths. And for example, it can be helpful for to monitor the deforestation that can happen in the south in this region. So for example, healthy green vegetation it reflects infrared wavelengths, and it can be differentiated from diseased or dead vegetation, which is probably black, and can help arborists understand and manage this forests better. So the same feature can be used to evaluate the size of rivers, lakes, ice covers, and so on and so forth. So interpreting SAR images can be challenging, as these images are affected by factors like speckle noise, geometric distortion, some radar-specific phenomena, and it also depends on the satellite system, data format, and software tools. So some commercial and governmental organizations, such as European Space Agency, provide user-friendly platforms for assessing SAR data. However, research laboratories usually work on enhancing existing algorithms and customizing them according to their needs. And among these laboratories are Remote Sensing Lab, which is hosted by EOS, by Earth Observatory of Singapore, and the Center for Remote Imaging Sensing and Processing, which is hosted by NUS and which is in short, CRISP. So can we go to the next slide? Another technology that is being used for surfacing the Earth the conditions is LiDAR, this active remote sensing technology, and it uses laser scanning to create three-dimensional images. can put this way. It is used for plant species classification, for conservation, geology, and military needs, obstacle detection, and so on and so forth. What is not so good about LiDAR, that it can act only in sunny weather, when it's unclouded, and only during the daylight. So this is the major shortcoming of this technology. However, it allows to create the images with higher resolution. So in the context of SAR satellite imagery, so some value-added services that are enhanced by AI can be the following, can be provided through the data fusion. So this is combining SAR data with other types of satellite imagery, like optical, multispectral, or with other data sets, for example, weather, topographic, demographic, and so on. Another approach can be time series analysis, and this is analyzing the changes in SAR data over time to identify trends. And it can be useful in monitoring the land use changes, infrastructure development, and any other long-term projects. So advanced processing and analysis is useful through the application of sophisticated algorithm, machine learning, and AI techniques to SAR data to extract higher level insights or identify the patterns. And finally, so the customized visualization can be useful for the customers, for the clients who utilize this data, and it just creates tailored visualization maps or reports. And finally, the decision support. This is really high-level AI integration of AI tools into the data sets provided by the satellites, and it aids in decision-making processes for various applications, such as, for example, natural resource management, urban planning, or emergency response. So can we go next? So first we spoke, so satellites that we mentioned were mostly satellites from LEO, from low Earth orbit. So there are other types of satellites that monitor Earth. For example, weather satellites. It is primarily used to monitor weather and climate on the Earth. They can be polar orbiting, or they can be geostationary. Geostationary, you remember, this is 36,000 kilometers over the Earth. So observation is typically made through the electromagnetic spectrum, in particular the visible and infrared portions. So it can be used for the snowfield monitoring, pollution, sand, dust, ocean. It can help observe the formation of the hurricanes, or the typhoons, El Nino, and so on and so forth. So while geosatellites are reliable and offer full coverage of the Earth, their spatial resolution might be lacking. As I mentioned, it's around 50 meters compared to the resolution provided by LEO, which is 50 centimeters. So this is the area where the LEO satellites can actually occupy the niche. So there are other satellites, both LEO and GEO, that monitor greenhouse gas emissions by measuring, for example, infrared wavelengths or using lasers. And on the image on your right, you can see the CO2 concentration captured in July 2024 in Jakarta and produced by OCO3 sensor, which is currently at the International Space Station. So yeah, can we go next? So far we have spoken about data collection. So now what about the data translation and how AI can aid in looking for patterns? So we have already mentioned the implementation of geospatial foundation models. This is combining remote sensing with aerial images and news reports. We mentioned integration of SAR and global navigation technologies, like combining the data from satellites in LEO and GEO. What we haven't mentioned yet is real-time on-board processing. This is actually the analysis of data on specialized hardware devices in real time without the delay. It allows for more efficient use of satellite capacity. It avoids spectrum congestion, but it leads to the loss of original data most often. Space-based data center, this is a novel solution to the problem of data transmission. What currently, to mitigate this data transport challenge and reduce the lag, these space-based data centers based on satellites can be put on the orbits. So satellites Other satellites will continue gathering information in space, but instead of sending raw data down to the Earth, they will send them back to the data centers, and it will process there, and only final relevant insights will be sent to the Earth. Okay, then super resolution satellite imaging, and this can we go to the next slide. This is a technique that uses image processing algorithm to improve the resolution of satellite images. So super resolution uses algorithm to reconstruct a high resolution image from one or several low resolution images of the same scene. And here in the picture, you can see some AI techniques that have been applied to process the image of Budapest. Again, can we go to the final slide? Finally, hybrid AI. This is a big thing that is happening currently in Singapore, and there are a lot of academic centers and academics who are working on developing the hybrid AI approaches. So what is this? This is basically the combination of big data and physics-based models. So you know about the traditional solutions when climate modeling was done through physics-based models. Through the systems of differential equations from the laws of physics, fluid motion, chemistry, and so on and so forth. But now it is combined with a data-driven approach for climate processes, for climate modeling. So picture the image A that you can see actually describes the physicizing a deep model by adding one or several physical layers after the layer of a neural network. And in image B, you can actually see the real example of prediction of sea surface temperatures, where a motion field of the water is learned with a convolutional deconvolutional neural network, and the motion field is further processed with a physical model to predict future states. So this is all from me about the technology, about space and AI. So here to you, Carol.
Thanks, Yuna. That's the last slide from Yuna, but we still have a couple more from me. Please hang in there. So in our analysis, we found that there's some synergy among the public, private, and academic sectors. And although this synergy is not perfect and there is room for improvement, especially from the perspectives of some private sector experts we interviewed. So Austin, Singapore Space Office, plays a key role in keeping the ecosystem together. As I mentioned earlier, it is a funded space office receiving 150 million Singapore dollars. So this would translate to around 100 million USD roughly to manage for the Space Technology Development Program. And this makes Austin not just a funded organization, but a funding organization as well. So Austin provides grants for startups, but typically because this is government money, the funds should trickle down to groups with a public component to it. And this is where the universities come in. So private sector companies can then team up with or support activities within the universities to be able to get access to these funds. And this actually helps everyone because collaboration is alive and the space agenda is advanced. So a couple of these projects, Yuna touched on these, also involve the integration of AI in space, typically solutions for persistent challenges such as navigation, inter-satellite communication, and space, what they call the space situational awareness, which is actually the ability to monitor, understand, and predict the activities and conditions in outer space. Now, the private sector not just works with the space office, but there's also some collaboration between private companies and the Singapore Civil Defense Force on disaster management technologies. Additionally, a private sector expert who also hosts a SaaS or software as a service platform for satellite data says that they are dedicated to breaking down these data silos by providing access to public defense companies and private enterprises, both locally in Singapore and internationally as well. So their company actually has an ongoing collaboration with defense agencies and enterprises across Southeast Asia. So you see here like the public-private partnerships transcend Singapore borders to include neighboring agencies as well. Okay, so aside from the support from the public sector and collaboration with the private sector, Singapore's academic community benefits from the collaborative nature of a number of international space initiatives. So our academics play a pivotal role by partnering with various agencies to create natural hazard forecasts, develop mitigation plans, and assess the impacts of climate change for global organizations. So, for example, the EOS RS Lab in NTU and CRISP of NUS play crucial roles in accessing and processing remote satellite data very swiftly. So CRISP of NUS utilizes its extensive expertise in operating high-performance antennas, while the EOS Remote Sensing Lab provides vital geospatial information to support disaster response efforts, and Yuna showed you a really good picture of that earlier. So another example was, for instance, after Super Typhoon Rai, or locally known as Odette, struck the Philippines, EOS-RS was able to produce flood and damage maps within a week for the UN World Food Program and more locally for the Manila Observatory. So they also collaborate with the AHA Center, the ASEAN Coordinating Center for Humanitarian Assistance, on disaster management, and also the Asian Disaster Preparedness Center to improve mapping products, making them lightweight and more accessible for responders with limited internet access, especially in the region. So EOS-RS also works with JAXA, the Japan Aerospace Exploration Agency, for satellite data. CRISP, on the other hand, works with NASA, the European Space Agency, or ESA, and also with JAXA, among other agencies, to control environmentally sustainable practices, for instance, to look at marine and air pollution. Okay, so as for opportunities and challenges for the Singapore case, so sustainability emerges as a strong driving force, with AI being leveraged for applications related to space sustainability by prolonging satellite data and maintaining inter-satellite communication and space navigation, as well as Earth sustainability by monitoring climate change impacts and supporting humanitarian assistance and disaster relief. So Singapore also has much potential, as Yuna has mentioned, to specialize in equatorial data collection and analysis. So it has a strategic location and advanced satellite capabilities. And of course, while there are challenges such as the spectrum congestion, which is everybody's problem, data gaps and susceptibility of the hardware to the harsh environments in space, AI can come in and attempt to mitigate some of these using AI techniques such as the super resolution onboard processing and geospatial foundation models. But in order to make this happen and to sustain the momentum, we also need sustained public sector support and funding for experimental AI. So some members of the private sector think they should be getting more support in order for them to be able to scale AI and space technologies and to drive costs to a minimum if they are to look at actual commercial viability. So for challenges, there are actually two gaps that we found in our analysis. First is a data gap across sectors, as not everyone is keen to share their data, and this can slow things down and likely cause duplication of efforts, drive experimentation costs up, and instead of having, the more targeted and more sustainable activities. So the second gap is talent gap, which is quite common in tech, like AI or space. But if you intersect AI and space, then the pool gets actually even smaller. And one thing that's worth mentioning for AI in space is that Singapore has quite a robust AI strategy, which was initially launched in 2019 and enhanced in 2023. And the hope is that eventually the national AI strategy will feed into the space ecosystem, especially since AI Singapore, which coordinates AI efforts across institutions, and Ben here is part of, They offer apprenticeship programs to train local talent. But, you know, the national AI strategy has AI's interest at its core. And if we want to advance the space agenda, we cannot rely on spillover effects from efforts for AI specifically. So we recommend that the space strategy should include incentives for space careers and also include like up or reskilling of mid-career professionals, for instance, upskilling space folks with AI and vice versa. So I think I gave it away. We were mentioning earlier that there's a missing key component in the Singapore space ecosystem, which we think is a national space strategy. So while there have been speeches from government officials about the direction of space technologies in Singapore, one of our interviewed experts confirmed that yes, there is yet to be a published national space strategy for Singapore. So we don't have it as an official document yet. Similar to the country's national AI and even a national quantum strategy, which arguably quantum is even more emerging than space. So based on the results of our report, we propose that Singapore should have an upcoming space strategy and must ensure that the country employs responsible and sustainable space activities through regulatory oversight, moves toward an innovative edge in space technologies, beginning with AI and space applications, establishes a collaborative, supportive, and shared platform between public, private, and academic sectors, and facilitates and incentivizes data sharing, and finally nurtures space talents and builds capacity within the country. So recommendations from other well-established space agencies and lessons from national space strategies can likewise prove to be useful. So consultations are great and are actually necessary, but even for us as researchers, as we reviewed other national space strategies, we found them already quite useful. So for instance, national strategies like that of the US and EU would focus mostly on applications for security and military purposes and some commercial activities, while public agencies such as ESA and NASA mention continuous collection of climate-related information as their main objective. So learning from both camps, Singapore can cover both traditional and non-traditional security aspects in its space strategy. So the upcoming strategy can additionally contribute to advancing space efforts in the region, in the Southeast Asian region, especially since Singapore has long-standing academic, private, and public collaborations with suppliers of satellites and data. So this comes from Europe, Japan, UAE, some regional observatories, and also some beneficiaries of space technologies such as JICA or the Japan International Cooperation Agency, the AHA Center, the UN World Food Program, and some regional governments, among many, many others. So Singapore has already deployed satellites that collect local climate and weather-related data, monitored unsustainable practices, and identified disaster-stricken areas to quickly divert resources in the region, playing an important space role in the ASEAN region. So with high connectivity with other regions, digital competitiveness, and access to investment, Singapore lays the ground for a holistic space strategy. Okay, so in conclusion, Singapore has much potential, but it really needs a national space strategy to help advance its agenda. We strongly suggest that the strategy should be on the horizon to consolidate the main players and also align Singapore's efforts in addressing global challenges such as climate change. So AI in space should be an integral part of the strategy if Singapore wants to gain and sustain momentum toward cutting-edge space technologies in the country. So we thank you for your attention.